Hello and welcome to Examine Earth. Today we're going to journey to some of the most interesting places on our blue marble. We will journey to the highest highs, the lowest lows, and the deepest deeps, and see how tectonic forces have shaped the world around us. The rocks and landscapes are trying to tell us a story if we know how to read them. There's so much to see when you take some time to examine Earth. For our virtual journey today, we will be using Google Earth, which is a freely available program, web app, and even mobile app. I'll also provide a list of our destinations in the description below, so you can enjoy the tour at your own pace. All aboard, the world tour starts now. We will begin our tour with the Google Earth Pro interface. If you download the Pro program, you get some more advanced features, but most things are available on the web and mobile apps too. You can navigate around by clicking and dragging. You can zoom in or out using the mouse wheel, pinching on your phone, or with the slider bar up here. Let's zoom out and see our planet in all its glory. Behold spaceship Earth, where we all live, separated from the cold, dark void of space by this thin little rind of atmosphere. Perhaps we should take better care of that, but anyways, that's another story. Let's head to the first stop, the highest point on Earth. Whoa, here we go, hold on tight. Zooming out a bit, we can see this complex network of valley glaciers in the high Himalayas. Zooming out a bit more, we can see the stark contrast between the drier highlands and the wetter lowlands. The massive mountain range is feeding water and sediment into one of the largest river systems on Earth, the Ganges and Brahmaputra rivers, emptying into the Bay of Bengal. Zooming out a bit more, we can see that the Earth is literally buckled and folded, not just the Himalayas, but the Suleiman Mountains of Pakistan in the west and the Arakan Mountains of Myanmar in the east. As the Indian plate collided with the Eurasian plate, neither continental plate subducted, but they crumpled up like pushing a carpet across a waxed floor. The rocks have been thrust so far upwards that the upper portion of Mount Everest, the roof of the world, is composed of marine limestone. Rocks and fossils from an ancient shallow sea have been lifted skyward, 29,032 feet above sea level, just shy of the cruising altitude of modern commercial aircraft. For our next stop, let's get low. Here is the lowest point in North America, Death Valley. Sounds very pleasant. Not only is it low, it's also dry. There are a few slightly lower places on Earth, but the geology here is more obvious. If we zoom out a bit, we can see that Death Valley is not alone. It lies within a series of valleys and ridges known as the Basin and Range. You can see this strange north-south oriented pattern that kind of looks like tiger stripes or stretch marks. The entirety of this area has been stretched, probably doubled in width. The precise cause of this extension is still debated, but likely has something to do with the now subducted Farallon plate and mantle heat flow. Speaking of heat, Death Valley also claims the current officially recognized air temperature record on Earth at an astounding 134.1 degrees Fahrenheit. Yikes, let's go somewhere a little bit cooler, but let's stay in California. Up to this point on our tour, we've seen plates diverging apart to make valleys, converging together to form mountains, but sometimes they slide past each other in a more glancing blow. Here we can see a long scar on Earth's surface. We can see from the color that it's pretty dry here too, but there are some rivers. If we look closely at this particular river, we can see that something is a bit odd. It looks to be bent. The scar is the San Andreas Fault, which is actually a series of faults where the Pacific plate and North American plate are neither coming together nor apart, but sliding past each other. We can see that this river has actually been offset across the fault as the plates slid, The distance here is almost half a kilometer. The river used to be straight, but over several seismic events, the southwest block has moved to the northwest, while the other block has slid to the southeast. Looking across the fault, each block has moved to the right of the other. San Diego, Los Angeles, and Santa Barbara are sliding past San Francisco and the rest of California, really the rest of North America. Now let's go somewhere a lot deeper, a lot cooler, and a lot wetter. Whoa, and here we are. The Challenger Deep is the deepest point within the deepest ocean trench, the Mariana Trench. It's named for the HMS Challenger, which was one of the earliest voyages attempting to map the seafloor. This crescent-shaped trench forms where the Mariana microplate meets the Pacific plate. Unlike when two buoyant continental plates collide to form high mountains, denser ocean plates collide to form deep trenches. In this case, the older, colder Pacific plate, far from the Pacific rise, subducts beneath the younger, hotter, and thus less dense Mariana. The Challenger Deep is a truly challenging place. The water depth here is an astonishing 35,800 plus feet, which equates to about 1,000 times atmospheric pressure. The water is also just above freezing, except near the scattered hydrothermal vents, where it can be well over boiling. Up until 2020, the list of people that had descended the Challenger Deep was shorter than the list of people who had walked on the moon. But even in these extreme conditions, creatures were spotted. Life finds a way. We've toured soaring mountains and abyssal depths. Now let's go somewhere a little flatter. Moving along, moving along, moving along. Welcome to Uyuni, the largest salt flat on Earth. It's called a salt flat because it's composed of salt and it's flat. Uyuni is so flat that on the rare occasions that it rains, the surface becomes a gigantic mirror. Zooming out, we can see that, like the smaller Bonneville salt flats in Utah, water and minerals flow into a closed basin, but there is no outflow. The water evaporates away and the minerals, primarily salt, are left behind. In the case of Uyuni, there's also an untapped deposit of lithium below the salt layers. Lithium's an important component in batteries and electronics, and demand is increasing. The old expression, if you can't grow it, you gotta mine it, applies here, but it would be at the expense of this unique environment. I'm feeling parched, so let's head somewhere a little bit more hospitable. And here we go. We are here at the Mid-Atlantic Ridge. Zooming out, we can see precisely why they call it that. The ridge lies at the midpoint of the ocean. The puzzle-like fit of the continents on both sides of the ocean was one of the earliest hints at continental drift. If we pan south along the ridge, we can see the fracture zones where the ridge jumps over. We can also see that this ridge joins into a series of other ridges that go along the Earth like seams on a baseball. These ridges are where brand new baby ocean crust is being formed. Now, of course, the Earth is not getting any larger, so if we're making new crust here along the ridge, we must be destroying old crust somewhere else, like the Mariana Trench. Unfortunately, the mid-ocean ridges are deep below the waves, but there is one place where we can see it high and dry. Here we go. And here we can see a deep scar cutting across the surface of Iceland. If we zoom out, we can see that scar moving across the entire island. And we can see the ridge to the north, and we can see the ridge to the south. The island lies directly on top of the ridge and also on a mantle plume hotspot. This gives Iceland its famous hot springs, and the increased volcanism has pushed it above the waves. This long, deep scar across the island is the boundary between the North American plate and the Eurasian plate. Many tourists seek out this area since it's one of the very few spots on Earth where you can walk across a tectonic plate boundary. So this is the middle of the Atlantic, but what about the Pacific? Here we go over to the other big ocean. The Pacific has its own ridge, although it's a bit less steep and a bit less ridgy and a bit less pronounced. So it's called a rise, not a ridge. The faster spreading rates of the Pacific make the young, hot, buoyant rock a bit more spread out. The Pacific rise spreads apart at about the rate that your hair grows, a few tens of centimeters per year, while the Atlantic Ocean is opening at about the rate your fingernails grow, a few centimeters per year. Of course, over millions of years, even those fairly slow rates add up. If we pan west a bit, we can get a sense of just how massive the Pacific Ocean is. It covers nearly a third of the Earth's surface, more than all of the land mass combined. So the ocean crust at the margins of the ocean has traveled a long way from the rise, and it took a long time to get there. Unlike the Atlantic, which is still opening, the old, cold, and dense Pacific crust is being subducted all around the so-called Ring of Fire. As the ocean crust sinks into the hot mantle, it dewaters and melts and forms volcanic arcs and island chains. Old crust destroyed at the edges and new crust created in the middle, and so it goes, not just in the ocean, but also on land. Here we are in Eastern Africa. If we zoom out a bit, we can see the Red Sea, which is a relatively young ocean basin where the Arabian Plate and African Plate have separated. A bit to the south on the continent of Africa itself, we see a long series of ridges and deep valleys. This is called the Great Rift Valley or East African Rift, which is really a series of rifts. Some of the more southern valleys hold some of the largest and deepest lakes on Earth, Lakes Malawi, Tanganyika, and Victoria. These lakes are so deep because the African Plate is ripping apart into what will eventually become the Nubian Plate, most of Africa, and the Somali Plate, the so-called Horn of Africa. As the rifting progresses, these lakes will connect up to the ocean, as the Red Sea has already done, and Africa will split in two and drift away from each other. Eventually, these continents will drift into other continents, and that brings us briefly back to the Himalayas. India broke off from Africa, along with Madagascar, in a very similar fashion. It took a little over 100 million years to drift northwards to its present collision with Eurasia. So that's the cycle. We see continents rift apart, small seas form, small seas grow into large seas close, continents collide, and then they rift apart again. Pangaea was not the first supercontinent, and it will not be the last. Plate tectonics continues to shape and reshape our world. Let's see what will eventually happen to the mighty Himalayas. Here in the eastern United States, a little bit closer to home for me, we can see that the crust is buckled and folded in a similar manner to the Himalayas. However, nobody would mistake the Appalachians for the Himalayas. The Appalachians are mere foothills in comparison, but still formidable enough to have shaped the entire history of the United States. So what's the difference? Well, both mountain chains resulted from the same continent-continent collision processes, but the Appalachians are much older. The rugged, jagged peaks of the Himalayas are still being actively uplifted today. However, the Appalachians formed over 250 million years ago when Africa and Europe collided with North America. The Appalachian Mountains were formed when Pangaea was formed, and they would have likely been even taller than the Himalayas are today, but they've been eroding away ever since. In places, tens of kilometers of rock have been removed, and we can get glimpses deep into the roots of these ancient mountains. Eventually, even the Himalayas will suffer the same fate. What goes up must come down. Raindrop by raindrop, sediment grain by sediment grain, the highest mountains are reduced to sand and mud and washed into the sea. I've included a few more interesting stops on the tour, but this feels like a nice place to wrap up our journey together. If you want more information on geology, up here somewhere, I've added a link to my video within the free dinosaurs course. I'll also provide a link in the description below. If you've enjoyed this video and like to see others like it, please click the like button and subscribe to the channel. You can also let me know in the comments below what other topics you'd like to see. That's all for today. Thanks for stopping in to examine Earth.